Black holes are invisible parts of space created when a star dies. Their gravitational pull is so strong, they engulf both matter and light. NASA's Chandra X-ray telescope recently found ultramassive black holes that are 10 times larger than originally thought and are growing faster than the stars in their respective galaxies. The findings came from astrophysicists at the University of Montreal and the Institute of Space Sciences in Spain, who looked at 72 galaxies that all had supermassive black holes in their center, which most galaxies have. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. The origin of rare and elusive ultramassive black holes, UMBH, with MBH 1 × 10 to the power of 10 Sun, is an open question. Using the Large Volume Cosmological Hydrodynamic Simulation ASTRID, we report on the formation of an extremely massive UMBH with MBH 1 × 10 to the power of 11 Sun at Z2. The UMBH is assembled as a result of two successive mergers of massive galaxies, each with stellar mass m*3 × 10 to the power of 11 Sun, that also produces a bright, rare triple quasar system powered by 3 10⁻⁹ Sun black holes. The second merger of supermassive black holes, SMBHs, follows the first after 150 years. The merger events lead to sustained Eddington accretion onto the central SMBH, forming an UMBH in the center of a massive compact stellar core with m*2 × 10 to the power of 12 Sun. The strong feedback of the UMBH quenches the surrounding star formation to less than 10 Sun/year in the inner 50 kpc/H region. There are two more UMBHs with MBH 5 × 10 to the power of 10 Sun at Z greater than 2 in ASTRID, which are also produced by major mergers of galaxies, and their progenitors can be observed as quasar triplets of lower luminosity. The rarely observed quasar multiples can be the cradle of UMBHs at high redshift and likely end up in the center of the most massive clusters. About 700 million light-years from Earth, in the swirling heart of the brightest galaxy of a 500-galaxy cluster called Abell 85, sits the biggest ultramassive black hole we humans have ever recorded in our local universe, the Earth's 1 billion light-year backyard, weighing in at a record-breaking 40 billion solar masses. And on Tuesday, a team of astronomers said they'd peered through all that space twice the distance for previous direct black hole mass measurements just to find it. The astronomy team from the Max Planck Institute for Extraterrestrial Physics and the University Observatory Munich published its discovery and analysis of this unusual monster in the Astrophysics Journal. There are only a few dozen direct mass measurements of supermassive black holes, and never before has it been attempted at such a distance, the study's lead scientist Jens Thomas said in a statement. But we already had some idea of the size of the black hole in this particular galaxy, so we tried it. But how massive is 40 billion solar masses, really? For starters, a solar mass is an absolute unit. It's equivalent to about 2 × 10 to the power of 30 kilograms as a measurement. Just one single solar mass is about as heavy as 333,000 Earths. In November, scientists were stumped when they discovered a black hole so heavy it shouldn't exist. That one was just 70 solar masses, which is already twice as big as current astronomical theories can explain. To put it another way, the astronomers said the newly measured black hole is 40 billion times more massive than our Sun. The MPE said the discovery could change the way astronomers estimate black hole mass in more distant galaxies, where direct measurements of the stellar motions close enough to the black hole aren't possible. So, let it be known that I really don't like the term ultramassive black hole. Some astronomers have been labeling all black holes weighing more than 10 billion solar masses ultramassive black holes, reserving the more famous supermassive black hole term for black holes weighing between 1 million and several billion times the Sun's mass. However, there really isn't a fundamental difference between these black holes and supermassive black holes. They're simply the high mass tail of the supermassive black hole population. There really isn't a need to give them a specific name. With that said, these objects formed the same way supermassive black holes formed. And how did supermassive black holes form? PFFFFFT, we don't really know. Tons of papers come out every month proclaiming some new mechanism they could have formed by formation of a supermassive star that imploded. Primordial black holes left over from right after the Big Bang. Super Eddington accretion. Collapse of gas clouds due to the bars within bars instability, and so on. We simply do not have any data from the early epochs of the universe when supermassive black holes would have formed. So all we have for the moment are models and predictions. Generally, it seems the most popular hypothesis is that supermassive black holes were born already pretty big, e.g. 10,000 solar masses. This is because we see them arise shortly after the Big Bang, when there wasn't much time for them to grow. Under the standard models for accretion, you simply can't shove that much gas onto a black hole that rapidly without the radiation feedback blowing it back out. However, there are accretion flow configurations that would allow this limit to be exceeded, Super Eddington accretion. Personally, I am partial to the idea that supermassive black holes started out small and then grew rapidly through Super Eddington accretion. However, I must admit my attachment to this hypothesis is more emotional rather than logical. The supermassive black holes were born large hypothesis is most reasonable given the data, but there's something about the idea that they were born really small that I just find cute. It's like a giant monster that originally hatched from a tiny egg. Or a fish fry that's the one out of millions that manages to eat all the other fish and grow into a huge tuna. Alas, physics does not care about the narratives we have in our head. But we can still dream. Astronomers have taken the first ever image of a black hole, which is located in a distant galaxy. It measures 40 billion kilometers across 3 million times the size of the Earth and has been described by scientists as a monster. The black hole is 500 million trillion km away and was photographed by a network of 8 telescopes across the world. Details have been published today in astrophysical journal letters. Professor Heino Falk of Radboud University in the Netherlands, who proposed the experiment, told BBC News that the black hole was found in a galaxy called M87. What we see is larger than the size of our entire solar system, he said. It has a mass 6.5 billion times that of the Sun, and it is one of the heaviest black holes that we think exists. It is an absolute monster, the heavyweight champion of black holes in the universe. We investigate the nature of the relations between black hole, BH, mass, MBH, and the central velocity dispersion, sigma, and, for core-sursic galaxies, the size of the depleted core, RB. Our sample of 144 galaxies with dynamically determined MBH encompasses 24 core-sursic galaxies thought to be products of gas-poor mergers and reliably identified based on high-resolution Hubble Space Telescope imaging. For core-sursic galaxies, i.e., combining normal core, RB less than 0.5 kpc, and large core galaxies, RB greater than or equivalent to 0.5 kpc, we find that MBH correlates remarkably well with RB such that $m_\mathrm BH\propto R_rm B 1.20 PM0.14 $RMS scatter in log MBH of delta RMS tilde operator 0.29 dex, confirming previous works on the same galaxies apart from 3 new ones. Separating the sample into sursic, normal core and large core galaxies, we find that sursic and normal core galaxies jointly define a single log linear MBH. Sigma relation MBH is proportional to sigma 4.88 plus or minus 0.29 with delta RMS tilde operator 0.47 dex. However, at the high mass end, large core galaxies, for with measured MBH, are offset upward from this relation by 2.5 to 4 times sigma s, explaining the previously reported steepening of the MBH sigma relation for massive galaxies. Large core spheroids have magnitudes MV less than or equivalent to minus 23.50 mag, half-light radii read greater than or equivalent to 10 kpc, and are extremely massive, M** greater than or equivalent to 1012 m. Furthermore, these spheroids tend to host ultramassive BHs, MBH greater than or equivalent to 1010 m, tightly connected with their RB rather than sigma. The less popular MBH-RB relation exhibits tilde operator 62% less scatter and log MBH than the MBH-sigma relations. Our findings suggest that large core spheroids form via multiple major dry merger events involving super/ultramassive BHs, consistent with the flattening of the sigma-LV relation observed at MV less than or equivalent to minus 23.5 mag.